Okay, so today we are doing a deep dive into, well, the world of pure abstraction.
Right, because AI is now tackling highly complex theoretical mathematics.
And not just tackling it, but achieving a kind of conceptual mastery. But the real story here, the thing that caught my eye, is the efficiency.
Exactly. We're talking about an AI cracking PhD level math problems, without needing a whole data center to do it.
So our focus today is on this new model, Seed Prover 1.5.
And it's a formal theorem proving model. It isn't just reading a theorem and spitting out an answer. It's mastering undergraduate and even PhD level formal proofs.
Which means it promises superior performance while using a substantially smaller computational footprint.
That's the claim.
Wait, so we've solved difficult math and cut the energy bill? That sounds almost too good to be true. Okay, let's unpack this a bit.
Yeah.
How does it actually solve these deeply abstract problems with that kind of rigor?
Well, the key thing to understand is the difference between natural language and formal proving. LLMs, large language models, are great at natural language. They can write a proof that sounds totally logical to a person.
But it might not actually be correct.
It might not be. But formal proving, especially in a language like Lean, it demands absolute step-by-step rigor.
I've heard Lean is like an incredibly strict coding language, but for math.
That's a perfect way to put it. One misplaced comma, one tiny, faulty logical leap, and the whole proof it fails. It's totally unforgiving.
And that's what traditionally makes automating it so computationally brutal.
Exactly. So CProver 1.5 needed a completely different engine.
Which is where the reinforcement learning comes in.
Precisely. The core method is this large-scale agentic reinforcement learning, or RL.
So instead of just learning from a textbook of already solved proofs.
Right. The model is constantly accumulating experience. It does this by interacting with formal tools like Lean over and over again.
So it's like a math student playing millions of little abstract games.
That's it. And the goal is to complete the proof. But every single move it makes has to be formally, provably correct. That formal feedback loop is what dramatically boosts its capability and its efficiency.
I see. That distinction is huge. But hold on. If the training is that intense millions of these self-corrected games, doesn't the final proof generation part become a bottleneck?
And that's where the efficiency hack comes in.
The test time scaling workflow.
That's the critical bridge, yes. The TTS workflow is sort of the application layer. Because the model has this really robust internal experience from all that RL training, it can leverage new advances in natural language, proving to bridge the gap.
It translates our sort of human intuition into that rigid formal structure.
And with incredible speed.
Okay, here's where it gets really interesting for me. The proof is in the pudding, as they say, the results.
And they are pretty stunning.
Seed Prover 1.5 delivered superior performance, even with that smaller compute budget.
Yeah, take the undergraduate competition math. On the PutnamBench dataset, it solves 88% of the problems.
88%. Wow, that's near mastery of some really difficult material.
And that mastery scales up. For graduate-level stuff like the Fate H problems, it handles 80%.
And these are problems focused on verifying existing complex theorems, right?
That's right. But the big one, for me, is the PhD level, the Fate X benchmark.
Where it's not just solving knowns, it's discovering new mathematical lemmas.
And there, it solves a groundbreaking 33%. A third of top-tier frontier math problems. That's a massive breakthrough.
And there was a specific anecdote that really drives this home.
Oh, yeah, the Putnam competition. The sources say the system solved 11 out of 12 problems from the Putnam 2025 competition.
And the time it took?
Just 9 hours.
9 hours. That's,
Yeah.
Well, it's an inhuman rate of conceptual processing.
It really is.
So, okay, what does this all mean? The big picture. The takeaway for me is that this combination of learning from experience and that high-quality, unforgiving formal feedback, it's a really powerful recipe.
I think it suggests we've hit a new inflection point in machine reasoning. This type of agentic RL, validated by formal feedback, holds just immense potential for the future of formal math.
And it makes you wonder, doesn't it? If an AI can achieve this level of mastery and speed today, what previously unsolvable problems in pure mathematics might it unlock tomorrow? Something for you to chew on until our next deep dive.